Hello, this is Yadagiri from Reddy Department, Marri Laxman Reddy Institute of Technology and Management. So today we are going to discuss the AC circuits, lecture number 2. So the topics to be seen for today's class is average values, RMS values, form factor, peak factor, and the AC through pure resistor. So today's first topic is average value. So average value of an alternating quantity. So how to find alternating average value of an alternating quantity, and what is the definition and what is the general expression? Let us see now. So the first definition we will see first. The arithmetic average of all the values of an alternating quantity over one cycle is called its average value. That means here first we can see if we can take any alternating quantity. So let us take, I am taking as a sinusoidal alternating quantity. The quantity may be voltage or current. So if we want to find the average of that quantity, so what we have to do generally for finding the average values of any, like if we can see ages of some classroom, some people in the classroom, then how to find the average ages? Then we have to take all the all the ages of all the students, then divided by number of students we have to take. So in the same way here also in AC quantity, in AC circuits, if you want to calculate the average value of an AC quantity, then we have to take the instantaneous values of total cycle over a period of time. So that is nothing but arithmetic averages of all the values of an alternating quantity. For example, you can see from the instant to instant 1, 2, 3. So instant to instant. So we have to, let us take, these are the n number of instants let us have. Okay, so first we have to calculate the average of all the instants, means we have to add all the instants divided by total number of instants. Then we will get the average value. So the general expression for average value we can see here. Average value is equals to, so this is the general expression. The average value's general expression is area under one cycle divided by base of the cycle. So in general I can write that as, that is a x average of is equals to 1 by t. So that is 1 by t is nothing but total time period of the cycle. Okay, integral 0 to t f of t and dt, f of t into dt. So f of t is nothing but the function, either it may be voltage or current. Here in our AC circuits, the alternating quantity either voltage or current. Okay, so if you can take that average value of voltage here, for example, average value of voltage we have taken here. So that is V average is equals to 1 by 2 pi. So that means one complete cycle will gives here. So 1 by 2 pi integral 0 to 2 pi V d omega t, V d omega t. So here average values we are having for symmetrical waveforms. Average value we have to calculate it only for half cycle. So this expression is valid. The general expression, this expression is valid for, this general expression is valid for all waveforms. For symmetrical, the average value will be 0, because positive half cycles, whatever the positive quantities are there, the positive instance, the same negative instance. So average value of the over one complete cycle will be 0. So this expression, whatever the expression we have seen for the average value, so that is, it is valid for all the waveforms. For symmetrical waveforms, the average value calculated over a one cycle will becomes what here, equals to 0. So why? Because positive area cancels the negative area here. So that means here you can see here. So during the complete cycle, you can see this is the complete cycle from 0 to 2 pi. So from 0 to pi, it is a positive, it occupies the positive area, and from pi to 2 pi it occupies the negative area. So the average of this complete cycle, that means here this is one complete cycle here. So average of this complete cycle will be 0 for symmetrical waveforms. So that's why for unsymmetrical waveforms, the general formula you can see the general expression for average values, that is 1 by t. So or we can say that 1 by t integral 0 to t. That means we have to add up sum of all the instantaneous values and integrating over a period of time. Then we will get the average value. Okay. So for symmetrical waveforms, the general expression you can see, that is V average is equals to 1 by pi integral 0 to pi V d omega t. So V is nothing but the voltage here. So if this formula can be valid for I also, that is I average is equals to 1 by pi integral 0 to pi I into d omega t. I into d omega t. Okay, so average values also we have to, the average values of voltage and current also we have to find for different cases here. So first case I am taken as a sinusoidal current. So average value of sinusoidal current. So in this diagram you can see that current is varying sinusoidally. So I am taking the current waveform, the current expression I am taken as current I is equals to Im sin omega t. So that means here the sinusoidal functions general expression is I equals to Im sin omega t. If we can go for the V, that is V is equals to Vm, instantaneous values of V is equals to Vm sin omega t. Vm sin omega t. So here I am taken as a current here. So the waveform I am taken as a sinusoidal current here. So the average value of complete cycle I am not taking here because it is a symmetrical wave. So I am taking only for positive half cycle. So during the positive half cycle you can see here, that is the time period I am considering, that is the up to 0 to pi I am considering. So remaining pi to 2 pi we are getting the negative values. So I am considering this is only my time period here. So that is average, I average is equals to 1 by pi into 0 to pi I into d omega t. So in this expression we have to substitute the I value. So what is I value now? So I value is nothing but Im sin omega t into d omega t. So we have to integrate. So take this is a constant value. So that is maximum value you have to take outside here. So then we are getting as, so here I am doing that. So that is I am taking common Im by pi. So integral 0 to pi and sin omega t d omega t. So if we can integrate this sin omega t, so then we are getting that sin integration is minus cos. So and substitute the limits, that is upper limit and lower limit. Then finally we will get the answer as 2 Im by pi. So generally, so what is the average value now? So the average value of sinusoidal or alternating quantity in general we can take as 2 Im by pi. 2 Im by pi. So or 2 Im by pi or 0.637 Im, that is 0.637 times of maximum value. So that means here if you can take for V average also, so then V average is equals to the same thing, that is 2 Vm by pi. 2 Vm by pi. So that means the 2 by pi value is nothing but 0.637 times of Vm maximum value. So this is the average value of sinusoidal current. So next if we can go for the average value of full wave rectifier type outputs, then we can see in the waveform. So in this waveform the cycle is repeats from every pi radians. The cycle is repeats for every pi radian. So that means here we have to consider the time period is only from 0 to pi. The time period only we have to consider from 0 to pi, because every pi radians the cycle will be repeats. So I average is equals to Im by pi integral 0 to pi Im sin omega t into d omega. So here also for full wave rectifier type output we are getting the I average is equals to 2 Im by pi, which is nothing but 0.637 times of maximum current. Similarly, if you can see for the half wave rectifier type output. So if we can calculate what is the average value of half wave rectifier output, so then we can see. So you have to consider the first we have to take the total, what is the total time period. So in that time period we have to calculate the average value. So first we have to take the time period here. So you can see up to 2 pi the cycle will be repeats. Every 2 pi radians the cycle will be repeated. So this is the total time period of the cycle here. So up to this here. So we have to consider the t value is nothing but 2 pi here. So that is I average if you want to find for this waveform, that is half wave rectifier, then 1 by 2 pi integral 0 to 2 pi I into dt. So I is nothing but this Im sin omega t. Then substitute that I value in the above expression and substitute the limits here. So here I am taking, so we have to split this limits into two interval. From one is from 0 to pi and another is from pi to 2 pi. So here, so that is I average is equals to 1 by 2 pi integral 0 to pi Im sin omega t. So plus one more time is there, one more term is there, that is integral pi to 2 pi, integral pi to 2 pi Im sin omega t into d omega t. So that means here you can observe from the waveform from the interval pi to 2 pi, its value is 0 here, its value is 0. So because its average is 0 here, so we can calculate the total time, the average value over a period of cycle, that is 0 to pi only. So that is 1 by 2 pi integral 0 to pi Im sin omega t into d omega t. So if we have to simplify this one and substitute the limits, then finally we will get the expression as I average is equals to Im by pi. So the value of Im by pi is nothing but 0.318. So that is 1 by pi value is 0.318 times of maximum value we are getting here. So this is the average value of half wave rectifier. Similarly, V average is equals to Vm by pi in case of half wave rectifier type outputs. So that is equals to 0.318 times of Vm we are getting here. So this is the average values of sinusoidal, full wave and average values. Now coming to the applications where we can use this average values means we have to use it in case of like as a battery charging purpose, we have to use this average values. And second application is charge transferred in capacitor circuits. Charge transferred in capacitor circuits is measured by using average values. So that means how much amount of the capacitor is charged. So that can be measured with the help of the average values. Next one, last application is it is used in the case of analysis of rectifier circuits. See, actually this average values, RMS values, form factor, peak factor, it is used in case of a power electronic subjects. Those were these are EEE students are there. So in that in power electronic subjects, these average and RMS and form factor and peak values will be useful for them. And we have to study in AC circuits also. For power electronics also, we have to see the average, RMS, form factor and peak factors. Okay, so these are the applications of average values. Next, coming to the RMS value. So here the DC quantity is constant with respect to time, that is the quantity is not changing with respect to time, but AC quantity is changing with respect to time. So to distinguish both, we have to see one common effect. So that effect is nothing but heating effect. So to determine the RMS value of any quantity or effective value of any quantity, so first we have to see some one of the experiment here. So that means here one common platform is there. So that effect is nothing but heating effect. So to express the RMS value of any quantity, so we have to see one common platform. That common platform is the heating effect. So here I am considering one simple experiment here. So to explain the RMS value, so first let us consider. So here I am taking AC supply here. So AC supply. So it is and it is connected to, so two ways which I am taking here. So it is a position number 1. It is a position number 2. So here I am connecting one bulb here. So this switch is again it is connected to one rheostat and it is connected to one DC ammeter. It is connected to DC supply. So in this experimental setup, first let us take the switch is at position number 1. So that is switch is closed at position number 1. Then this whatever the current flows into this, let us take this is I am taking this as a bulb here. So here whatever the current flows into this bulb, so that is AC current. So how much of the brightness is given while you applying the AC supply, that we have to observe from this bulb. So later on, so we have to take that effect here, first one. Second one, again we have to switch the, we have to take the switch from second position. That means here we have to throw the switch from position 1 to position 2. So that means here, so we are applying DC supply to this bulb. Slowly we have to vary this rheostat here. So this is the variable rheostat, and we have to observe the what is the values of DC, what is the current flows into the device. So here we have to observe one effect here. We have to observe that at what value of the current will give the same brightness as that of the AC will give. So that value of current is nothing but RMS value of AC current. So that means here, so here in this also I am flowing, in this also the current flows here, DC current here. So the ammeter will reach the DC current here. So here if the equal amount of the, see here, whatever the amount of the time we are passed, AC current is passed now, the same amount of the time the DC current is also passed here. So that means here the same amount of the time. So whatever the time, for example, if I am taking here AC current is flows from some time here. So let us take here 5 milliseconds I am transferring the AC current to this bulb here. So in the same way, the same current has to be flows from the same time of the DC supply. So the current which is produced, so the current, the DC current is nothing but, so at which value? So at the whatever the DC current is nothing but the RMS value of AC current here. So that means here it is a steady current. Okay, RMS is a steady current. So whatever the brightness it is produced by AC, the same amount of brightness has to be produced by the DC. Then that at the equal amount of the time, then we can call that as a IDC is nothing but RMS value of AC current. So generally, so the generally we can define the RMS value here. So the effective or RMS value of an alternating quantity is that steady DC which when flowing through a given resistance here, you can observe here, which can flowing through a given resistance for a given time produces same amount of heat produced by alternating current flowing through the same resistance for the same time. So just now in this experimental setup also I told that. So first we have to apply the AC supply, then we have to observe the what is the brightness, then we have to apply the DC supply, then we have to, while applying the DC supply, when current is flows into that bulb through the resistor. So then at which value of the current the equal amount of the brightness will get, then that we can call it as the RMS value of AC current. So the general expression you can see here, or we can say that RMS value is nothing but the square root of area under squared curve by base. So this is the basic general definition of RMS value of any quantity we can see here. Okay, either voltage or current. So RMS value is nothing but the square root of area under squared curve divided by base of the curve. So this formula is valid for any waveforms. So the general expression for Vrms, if you can take here, that is Vrms is nothing but RMS value of the voltage. So that is 1 square root of 1 by 2 pi over a complete cycle you are taking, integral 0 to pi f square into d. So in general I can write this expression as, that is XRMS is equals to square root of 1 by t integral 0 to t f square, that is f of t square into dt. So this is the general expression for calculating RMS value of any quantity. So here t is nothing but total time period, okay, and this is a square of the mean value, or in general we can say that square of the mean value, or this is a total time period. So this is the RMS value of a quantity, the general expression. So now let us see the next one is RMS value of a sinusoidal current. So here in this waveform, so if you want to calculate the RMS value of AC current here, you can see sinusoidal current here. So as per our general expression, that is XRMS is nothing but IRMS. So here I am writing the general expression here. So that is XRMS is equals to square root of 1 by T integral 0 to T f of f square of T into dt. So this is a general expression for finding the RMS value. So based on this general expression, so x in the place of I is nothing but I am taken as IRMS. So that is IRMS is equals to square root of 1 by T. T is nothing but total time period I am taken here. So this is the total time period I am considering here. So for a total complete time period 2 pi, so integral 0 to 2 pi I square into d omega t, I square into d omega t. So substitute this I square I value, substitute here this I value, then we are getting as I square Im square sin square omega t into d omega t. And we have to simplify this expression, and we have to apply the limits over the limits and to cancel the squares and roots. And finally we are getting that IRMS is equals to Im by root 2. So the Im by root 2, or we can simply say that IRMS is equals to 1 by root 2 times of I maximum. So that is the value of 1 by root 2 is 0.707 times of maximum value. So in general, if you can apply for VRMS also, so VRMS is nothing but 1 by root 2 into Vm. Okay, so these are the general expressions for the RMS values of current and voltage for sinusoidal waveforms, for pure sinusoidal waveforms. So IRMS is equals to Im by root 2, VRMS is equals to Vm by root 2. Similarly, RMS value of full wave rectifier. So for full wave rectifier, here the time period we can take in as, that is so the each every cycle, the cycle will be repeat. So I am taking only the half cycle here. So IRMS is equals to the total time period, so that is pi integral 0 to t, that is pi Im square into sin square omega into d omega t. So we have to simplify this expression and take Im square common and substitute that formula, so that is sin square omega t into d omega t. Then finally, after simplification, we are getting the final expression as IRMS is equals to Im by root 2. So for full wave rectifiers also we are getting the same output, that is same value, that is 0.707 times of Im value we are getting for full wave rectifiers. So coming to the RMS value of half wave rectifier type inputs here. So for half wave rectifier type inputs, you can observe here. So the time period is total 2 pi radians here. So this is the total time period. So that's why we have to take in this is IRMS is equals to 1 by t, that is t is nothing but 2 pi here. So 0 to t, that is 2 pi, that is I square into d omega t. So here we can get, after simplification, all these expressions, above expression, then we are getting is RMS value of half wave rectifier. RMS value of half wave rectifier type we are getting as Im by root 2, that is 0.5 times of maximum value. So these are the RMS values of sinusoidal, half wave and full wave rectifiers. So next definition is the form factor. So the definition of form factor here, the ratio of RMS value to the average value. The form factor is nothing but the ratio of RMS values to the average value of an alternating quantity is known as form factor. So the general formula here, the form factor is equals to RMS value divided by average value. So peak factor or crest factor is nothing but The peak factor is nothing but it is the ratio of maximum value to the RMS value of an alternating quantity is known as peak factor or crest factor. So the maximum value, the ratio of maximum value to the RMS value is known as the peak factor or crest factor. So these factors will be helpful for calculating the sinusoidal varying in AC through pure resistor, inductor and capacitors. And these factors is also useful in the power electronics application when you are doing studying in the power electronics subject. So now we will see the form factor and peak factor for different values here. So for sinusoidal waveforms, so previously we have calculated that I average is equals to 2Im by pi. 2Im by pi. So that is its value is equals to 0.637 times of maximum value, and IRMS also we have calculated Im by root 2 for sinusoidal waveform. So that is 0.707 times of maximum value. So form factor, the formula, the definition just now we have seen that the form factor is nothing but RMS value of the RMS value divided by average value. So what is RMS value of current here? So this is the RMS value of current. And what is the average value of current? This is the RMS value. That is the RMS value of current is equal divided by average value of current. So if you can simplify this, Im will get cancelled here. So the value of the 0.707 divided by 0.637 will get the form factor as 1.11 for pure, that is for sinusoidal waveforms. So for sinusoidal waveforms, the form factor is 1.11. This is very, very important. Next, coming to the peak factor or crest factor. So the peak factor is nothing but maximum value, the ratio of maximum value to the RMS value. So the maximum value and RMS value is nothing but 0.707 times of maximum value. So Im will get cancelled. So the ratio of 1 by 0.70 is nothing but 1.414 times. So this is the peak factor or crest factor of a sinusoidal waveform. Coming to the full wave rectifier output. So full wave rectifier output. So just now we have seen that for full wave rectifier outputs also we have seen the average values and RMS values. So we have seen average values, RMS values. So then form factor, we can see here the form factor is nothing but the ratio of RMS to the average value. Then here also we are getting the same result, that is form factor is equals to RMS by average values. So the value is equals to 1.1 times. Similarly, if you can calculate for IRMS is nothing but IRMS is equals to 1.11 times of I average. 1.11 times of I average. So this is the IRMS value, or VRMS is nothing but VRMS is equals to 1.11 times of V average. Coming to the peak factor or crest factor of full wave rectifier circuit. So that is the ratio of maximum current to the RMS current. Then we are getting the result as 1.414. Next, coming to the half wave rectifier type output waveform. So for half wave rectifiers, we have just calculated the average values Im by pi. Its value is equals to 0.318 Im, and IRMS is nothing but 0.5 times of Im. So if you can calculate the ratio of RMS by average, so that is form factor, if we can calculate, then we are getting the result as 1.57. And peak factor is nothing but Im divided by IRMS. So Im is nothing but Im, and IRMS is nothing but 0.5 Im. So Im will get cancelled here. Then finally we are getting the peak factor as the root 2. 2 only. So these are the form factor, peak factor, RMS value, average values, definitions and expressions we have seen. So next we will go for the next topic, that is AC through pure resistor. So that means here we have to take one element here. So that is a pure resistors I am taken. So for this resistance I am applying the AC supply to that pure resistance. Okay. So here, so an alternating voltage I am applying here. So that alternating voltage is given by V is equals to Vm sin omega t. I am applying to pure resistance, that is R. So that means here pure resistance means what here? It is not containing any impurities. Okay, so the property of the resistance, as you already know, it opposes the flow of electric current. So that is a property of a resistance. Then current flowing to the circuit is given by, so the current, whenever we are applying the AC circuit, AC current, AC supply we are applied to the resistance, then current flows into the device, and that current is given by the current flows to the circuit is I, the voltage across the resistor. So this voltage across the resistor, that is VR, is given by I into R, okay, which is same as the supply voltage. So that means the voltage across resistor is equals to the supply voltage, which is same as the supply voltage. So using Ohm's law, the current flows through the device, the current flows in the circuit is given as current I is equals to V divided by R. So that is we can write the following relation here. So that is V equals to Vm sin omega t divided by R. So V is nothing but applied voltage here. So that is sinusoidal voltage we are applying. That is Vm sin omega t we are applied here. So that V is equals to Vm sin omega t divided by R. So here I can relate this as a standard relation here. So this is the standard relation in the voltage, and the standard relation in the current is equals to Im sin omega t. So in general we can say that the standard relation is nothing but the omega V equals to Vm sin omega t plus or minus theta, or omega t is equals to plus or minus theta. So this is the standard expressions for voltage and current. So plus or minus theta here, or sometimes we can say that plus or minus pi. So as you see, if we can compare both the voltage and current expressions here. So if we can compare the voltage and current expression. So first we will see what is the voltage expression we are getting here. That is voltage expression, that is Vm sin omega t we are applied to the circuit here. Then what is the current expression we are getting here? Current I is equals to Im sin omega t here. So as per our standard expressions, that is V and I. So as you see here, the angle, that is theta, or the angle phase angle phi, is equals to 0 here. So that is as you compare these two expressions, the phase angle we are getting as 0 here. So phase angle we are getting 0. So then what is the phase angle, and what is the phase angle between the voltage and current, I will explain in the coming sections. Okay. So meanwhile we can see here the phase angle for the voltage and current will be 0, because as per the standard expressions we compare the equation 1 and equation 2, then we can get that result as phi is 0 here. So then we can see the maximum value of the current is equals to Vm by R. So we can conclude that here few resistance, the voltage and current are in phase here. That means here the phase angle between them is 0. So as we can compare the both equation 1 and 2 with the standard equations. So these are the standard equations I am considering here. So while considering this equation 1 and 2 with the standard equation, I am make the conclude that the phase angle is equals to 0 here. So that means both are in phase here. So that means voltage and current will be in the same phase here. That means if the voltage started at 0 degrees, then the current is also started at 0 degrees. If the voltage is started at 30 degrees, then the current is also starts at same 30 degrees. That means voltage and current both are in same phase. That is, both are in same nature here. Okay. So here, so if you can see the phasor vector, so if you can see for the, you can see here. So this is the voltage and current both are in phase, same phase. That means here, if voltage starts at 0 here, as you can see, this is the vector diagram and this is the phasor, that is a waveform here. So for the waveform you can see here. Okay, so the waveform you can see, this is the voltage starts at 0 here. So it is attains in the maximum value, and again it is attains the minimum value in the positive direction, and again it is attains in the negative also. You can see here it is attains the negative maximum and attains the 0 here. So that means here voltage, you can observe here, it is varying sinusoidally. In the same way, the current is also starts at same phase here, same angle. That is, it starts at same degrees. That means here voltage, current both are in same phase. So that means here both are started at the same point here. So they attain the same maximum value. Again they attain the 0 value. Again they attain the 0 negative maximum. Again they attain the same. So that means both voltage and current are in same phase angle. They are moving at same angles. Okay. So next one. So from this, what I am conclude is that, so for AC through pure resistors, the voltage and current both will be in the same phase. The phase angle between them, so we can see that the phase angle between the voltage and current is equals to 0. The phase angle between the, because they are in same nature, the phase angle between them is 0. So coming to the power relation for AC through pure resistor. So the instantaneous power, we can see the product of voltage and current. So the product of voltage and current, we can see the V is nothing but, so just now we say from the equation 1, V is equals to Vm sin omega t, and from the second expression, the current I is equals to Im sin omega t, Im sin omega t. So the instantaneous powers is equals to Vm sin omega t and Im sin omega t. So take that Vm Im common here. So sin into sin square omega t. So sin square omega t we can write in the expression, we have to, that is 1 minus cos 2 theta by 2. So then the 2 is taken as a common, 1 minus cos 2 omega t. So this power can be divided into two components here. So one component is called, this is a constant power component, and this is the fluctuating, the second one is the fluctuating power. Fluctuating power means here it is the 2 times of omega is there. So that means here over a period of cycle we are getting the two frequencies here. So then what happened, the fluctuating power will becomes 0 here. The fluctuating power will become 0. So then what is the overall power here? So the power P is equals to, that is instantaneous power P is equals to Vm Im by 2. So I can write this as Vm by root 2 into Im by root 2. So then for what is the power in the resistive, pure resistive circuit means Vm Im is nothing but Vrms. Vm by root 2 is nothing but Vrms. Im by root 2 is nothing but Irms. So then in generally I can write this power expression, power P is equals to V into I in case of a AC through pure resistor. AC through pure resistor, the power P is equals to the product of Vrms into Irms, or V into I. So coming to the average power. So previously we have seen instantaneous power, now it is average power. So average power means just now we have taken over a period of cycle we have taken. So that is 1 by 2 pi integral 0 to 2 pi Vm Im by 2 minus Vm Im by 2 into cos 2 omega t dm. So if you can simplify, then here also we are getting the same expression, that is average power also we are getting as the same expression. Instantaneous power and average power will be same. So that is average power is the product of the RMS voltage and the RMS value of the current. So this is the average power and RMS power of instantaneous power and average power of AC through pure resistor. So the voltage and current waveforms are pure sinusoidally resistive circuits. Pure resistive circuits is shown here. So here you can observe that here the voltage, you can see here, this is the voltage, okay, and this is the current expression. So that is voltage and current both are started at same point here. So that is 0 degrees, and the that is, see here, if the voltage goes like this, then the same in the same direction the current is also flows. That means both are in same phase nature. So therefore the current direction, you can see here the current is also follows the voltage. Next, coming to the average power over a cycle, here you can observe here, this is the power V into I, that average of the voltage, that is the average power is equals to V into I, that is voltage multiplied with, that is Vrms into Irms. So therefore this is the average power we can see here. So average power is equals to, this is the V into I, the product of voltage and current. So during the negative half cycle also we are getting the same here, that is the average of the V into I. So that is a minus V into minus I, then we are getting the same result. So minus into minus plus, so that is Vi. So therefore the average power during the negative half cycle also we are getting this one. So the instantaneous power is always positive here. So the instantaneous power is always positive. That means here the power flows from, always the power is flows from source to load. Okay. So always you can see here the power is flows from source to load. So because power is positive, so during the positive half cycle or negative, during the negative half cycle also the power is positive. So that is instantaneous power is always positive. So the power is flows from source to load here. So the power is flows from source to load. Okay. So that's all for today. So next class we will meet.